I will discuss inflection points and concavity. A graph of a function y equal to fx is called concave up if it lies above its tangent lines, and it is called concave down if it lies below its tangent lines. So let's see this picture. So here, see this green line. So this is tangent to the curve, and curve is below this tangent line. So in this portion, from 0 up to this portion, so the curve always lie below this tangent line. Therefore the curve is concave down in this portion, and you will see that the curve is concave in this portion, and then the curve is concave down in the next portion. So see how the curve changes from this is concave down to it becomes concave up as it is now above the tangent lines. Now the curve will again come below the tangent lines. So curve is frequently changes into concave up, concave down, and so on. The graph might be concave down in one interval and concave up in the next interval. So a point where it changes from concave up to concave down, or from concave down to concave up, is called a point of inflection. For example, in this picture, the graph in the left of this yellow line, this graph is concave down, because if I draw a tangent line, the graph always lie below this tangent line, and see the right side, it is concave upward because the graph is always above this tangent line. Now, how to find type of concavity? So if we have a function y equal to fx and find its double derivative. If double derivative is positive on some interval, then the function is called concave upward, and if double derivative is less than 0, then it is called concave downward. So let's see what is the logic behind this rule. So notice that if a graph is concave up over an interval, then slope of the tangents increases as the curve progresses from left to right. Now see this thing. So this is a picture of a concave upward curve. I have drawn various tangents. So as I move in this direction, so this is one tangent, second tangent, third tangent, fourth tangent. So you can easily check that the slope of the tangent increases as I go in this direction. It means the slope function is a monotonically increasing function. But what is slope function? So derivative of the curve tells us the slope. So slope function is increasing, it means derivative of the double derivative must be a positive. So therefore double derivative is greater than 0. So this is justification of this rule. Similarly, we can show that if a curve is concave downward, then the slope function is decreasing, so its derivative is less than 0. Now, how to find point of inflections in a curve? So if we have a function whose double derivative changes sign as we moves from left of this point x naught to the right. For example, see again this curve. So here the double derivative has sign negative, and here the double derivative sign has positive. So when we move from left to right of this point, the sign changes. So the point where this sign changes is called a point of inflection. This change in sign of f double dash x on crossing x naught tells us the one side of the point, this the graph is concave down, and the other side it is concave up. So f double dash less than 0 means the curve is concave down in this direction and curve is concave up in this direction. The change in sign of f double dash on crossing x naught implies that fx is monotonically increasing or monotonically decreasing. So here f double dash x is negative, then 0, then positive. So f double dash function is monotonically increasing in this picture. So it could have happened that in this direction f double dash x might be positive, and here it's 0 and then it is negative. Then it would have been that f double dash x monotonically decreasing. So in both cases, either f double dash x in this interval is monotonically increasing or it is monotonically decreasing. F triple dash x must not be zero. This is condition for monotonically increasing or decreasing functions. So we have found a formula to find a point of inflections. The formula is the point of inflection can occur at those points of x where double derivative equal to zero, but must remember that not every solution of this equation is a inflection point. So to check whether the possible point is a point of inflection or not, we must see whether the double derivative changes sign from positive to negative or negative to positive in small neighborhood of point uh, x, that is whether this triple derivative is not zero. So second thing is, if double derivative is not defined, that point can also be a possible point of the point of inflection. So we shall find those points where the derivative is not defined and see the behavior of f double dash x in the right side and left side of this point. If the sign of double derivative changes in left to going from left to right, then we say the point x naught is a point of inflection. So see first example. So consider equal to x power 3 by 5. Its double derivative is minus 6 by 25 into 1 by x power 7 by 5. So this thing is not zero at any points, but this is not defined when we put x equal to 0. So something upon 0 is not defined. It means x equal to 0 can be a point of inflection. So see its behavior when x is little less than 0 and its behavior when x is little more than 0. So when x is less than 0, so it is this thing is negative and one negative sign is here. So the derivative becomes positive, and when this thing is positive, the d2y by dx square will be a negative. So it means in the neighborhood of 0, the sign of double derivative changes from positive to negative. Therefore x equal to 0 is a point of inflection. Example 2 is we have f of x is sine x. So we have its first derivative, second derivative, third derivative. So on substituting second derivative equal to 0, we see that x equal to 0, and triple derivative is not 0, so therefore 0 is a point of inflection. Similarly, this third example, fourth example, and more examples can be seen by visiting this website. Thank you very much.